Scientists just found out that the Earth's crust beneath the Marmara Sea is sending seismic signals that look exactly like the kind that show up before a major earthquake. An earthquake that can shake entire coastlines and send waves racing toward crowded cities. For years, scientists focused on visible ruptures on land because they could measure and map them easily. But now, they made a detailed map of a huge fault system under the seafloor. The Mediterranean already sits at a dangerous crossroads where massive tectonic plates meet. Those plates push, scrape, and stretch against each other, and that constant motion creates massive stress. The crust there grows thinner over time, and thinner crust means it can't absorb stress easily. Stress builds, pressure mounts, and the signals coming from below show that parts of this fault system have started to move in unusual ways. The new map shows that future large earthquakes may begin at the boundaries where weaker and stronger sections of the crust meet, or along edges of highly resistive zones. They even pinpointed one of the most likely locations, beneath the Marmara Sea. What makes this discovery so intense is the scale. The faults in the seabed form long corridors where energy can accumulate for decades or centuries. Scientists warn that this setup is the kind that can produce a super earthquake, a massive seismic event capable of shaking large coastal cities and possibly generating tsunamis. A tsunami forms when the seafloor shifts vertically and displaces huge amounts of water, so it looks really plausible in this setting. The water it sets free radiates outward in powerful waves that can cross entire seas. The Mediterranean holds dozens of densely populated shorelines, so it could affect millions of lives. Speaking of that, let's zoom in on Istanbul, Turkey's largest and most populous city. The massive fault line sitting right under it doesn't act the way scientists thought it did. For years, experts looked at the main Marmara Fault, a branch of the North Anatolian Fault running beneath the Sea of Marmara, and worried it might rip in one single monstrous rupture. That kind of break could unleash a megaquake in the high 7s or beyond. But when scientists ran detailed computer simulations covering more than 10,000 years of earthquake cycles, they saw something different. The fault doesn't behave like one giant zipper waiting to unzip all at once. It behaves more like a row of connected tiles that break in sections. And the reason comes down to what's happening miles below the seafloor. It's called rheology. Simply put, how materials deform under stress, how rocks bend, stretch, or snap when you squeeze them hard enough. Under the central Sea of Marmara, giant piles of compacted mud, sand, and debris sit on top of warmer crust. In those upper layers, the sediment usually deforms slowly and steadily, especially at shallow depths where pressure and heat interact in specific ways. Deeper down, higher temperatures weaken the rocks. Warm rock flows more easily than cold rock. That heat acts like a built-in brake system that limits how far a rupture can tear through the crust. When researchers built a 3D earthquake cycle model, they fed in real heat flow measurements, rock friction data, and structural details, and replayed thousands of years of seismic activity. When they included both sediment thickness and temperature differences, the model finally matched history, including the powerful quakes of 1766 and 1912. And none of the simulated events exceeded magnitude 7.3. That level of shaking can collapse buildings, fracture infrastructure, and cause landslides. But it differs from the nightmare scenario of one continuous coast-to-coast rupture. Instead, different sections behave in different ways. The western segments produce more regular earthquakes, including magnitude 7.2 events roughly every 150 years. The eastern sections generate smaller double quakes, back-to-back events between magnitude 6.2 and 6.8 about every century, and a magnitude 7.0 roughly every 500 years. Parts of the fault don't snap at all, but creep. Scientists call it shallow creep, which just means the fault slowly slides without producing a major quake. It releases tension quietly, like letting air out of a balloon instead of popping it. GPS measurements and clusters of repeating small quakes over the past 20 years confirm that slow slip near the central basin. So what does this mean for Istanbul? A city of over 15 million people sitting practically on top of this system. A magnitude 7 or 7.3 quake close to the city could still rock neighborhoods, especially if two strong events strike in quick succession. Infrastructure, older buildings, and densely packed districts are at the highest risk. The fault hasn't produced a major rupture in this section since 1894, which means there's more than 130 years of accumulated strain. The simulations show major events could strike in the coming decades. Then there's Santorini, where more than 28,000 earthquakes happened in just a few months in early 2025. Most of the quakes stayed small, but some reached magnitude 5, strong enough to fracture walls, rattle nerves, and push authorities to close schools and evacuate parts of the island. And this wasn't just tectonic plates grinding like they usually do. This swarm moved. The epicenters shifted gradually northeast toward the Colombo submarine volcano about 5 miles offshore. That migration told scientists magma was on the move. Researchers calculated that roughly 80 billion gallons of it, enough to fill about 120,000 Olympic swimming pools, surged upward from depths around 11 miles beneath the surface. It climbed fast, then stalled about 2 to 2.5 miles below the seafloor. And all this was going on along the Hellenic Arc, one of Europe's most active subduction zones, where the African plate dives beneath the Eurasian region. Earthquakes often migrate across that span toward nearby islands. History backs that up. The 1956 Amorgos earthquakes unleashed massive shaking and a tsunami across the region. So, when 28,000 tremors light up the seismic network, you pay attention. This episode changed how scientists understand volcanic swarms. Now they know magma can intrude, fracture miles of crust, reshape underground reservoirs, and still never surface. It can load the system for the future without pulling the trigger today. And that matters because when magma moves like this, it changes stress fields underground and how future quakes might breed. The good news is that scientists now have really cool monitoring tools that feed real-time seismic feeds, underwater pressure sensors, and repeated gas measurements near volcanic vents into integrated hazard models. If magma starts accelerating upward again, researchers will see it and will take action. And there's another bold new idea in earthquake and tsunami warning: using undersea internet cables for this purpose. Nearly 1 million miles of those fiber optic lines on the seabed were designed to carry data, but scientists discovered that they can also detect tiny changes in light signals caused by seismic vibrations. In simple terms, when the ground shakes, the cable feels it. And this could be incredibly useful because forecasting earthquakes, even on land, is tricky. In the ocean, it has felt almost impossible as you can't scatter thousands of sensors across the seafloor easily. But those cables already sit there, stretching across deep trenches and continental shelves. If researchers use them as sensors, they can monitor tectonic movement in real time across huge areas. For a region like the Mediterranean, with hidden faults, active volcanoes, and crowded coasts, that system could offer precious seconds or minutes of warning. Seconds sound small, but early alerts let trains stop, gas lines shut down, and people move away from immediate danger. The fiber optic cable used for Seafloor Project, or FOCUS in the short version, didn't warn anyone about real disasters yet, but it had 2 false alarms. It reacted to a submarine landslide and weight bags that pushed the cables down. It proves the system works and could be life-saving in case of real danger, especially in vulnerable regions such as the Mediterranean. It shaped civilizations for thousands of years, and now science reveals it still shapes itself. They can't stop tectonic plates or cool magma chambers, but they can understand patterns, reduce vulnerability, and design cities smarter. There's a giant crack hidden under the western coast of North America, and one day soon, it could trigger a catastrophe powerful enough to change the entire region within minutes. It's called the Cascadia Subduction Zone. This fault stretches from 620 to 700 miles, starting in Northern California, running past Oregon and Washington, and reaching up to Canada near Vancouver Island. This active region created the Cascade volcanoes, including Mount St. Helens, which erupted in 1980. Other giant eruptions happened there thousands of years ago too, including the one that formed Crater Lake. In this region, deep underground, huge pieces of Earth's crust are slowly pushing into each other, and one plate sliding underneath another. Normally they move very slowly, but sometimes parts of the plates get stuck. But the scary part is, the plates keep pushing away. Pressure is building underground for hundreds of years, and when Cascadia finally breaks loose, it can trigger one of the most powerful earthquakes in North American history. If it happened, the shaking along the coast could last for 5 to 7 minutes. Picture the ground literally rolling beneath your feet for longer than an entire song. Buildings would sway and collapse, roads would split apart, bridges would break down, and power systems would fail. But this devastating earthquake could only be the beginning. An enormous tsunami could hit the coast just 15 to 20 minutes later. In some places, the waves could reach around 100 feet high. That's taller than many buildings. Entire coastal towns west of Interstate 5 would be flooded or destroyed before people have time to react and evacuate. Even cities located further inland like Seattle, Portland, and Vancouver might be seriously damaged too. They're farther from the coast, so the shaking would probably be slightly weaker there, but still powerful enough to wreck older buildings, roads, pipes, and other infrastructure that wasn't designed for megaquakes. Tiny earthquakes happen under Cascadia all the time. Most people never notice them, but scientists can pick them up using sensitive equipment placed across the Pacific Northwest. Some of those quakes are really unusual, like a type called slow earthquake. Unlike normal earthquakes that hit suddenly, these move very slowly, deep underground. The movement can continue for days or even weeks. Nobody feels it at the surface, but far below, huge sections of rock are still shifting. The strange thing is that these slow quakes happen again and again in Cascadia, usually every 13 to 16 months. Scientists monitor them day and night because they happen in an area that can produce a devastating megaquake. The strongest activity is usually detected around northern Washington, Vancouver Island, and northern California. Cascadia also produces regular earthquakes, and some of them can be extremely destructive because they happen relatively close to the surface. Around 1,100 years ago, a powerful earthquake struck near modern-day Seattle. Parts of the ground suddenly rose several feet, and the quake triggered a tsunami. More recently, powerful earthquakes hit Washington state again in 1949 and 2001. Buildings shook, people lost their lives, and the entire region was seriously wrecked. Northern California is especially active because of something called the Gorda Plate. That's a cracked section of ocean crust that is being forced underground. The plate is literally bending and breaking under huge pressure deep below the coast. Interestingly, Oregon has fewer earthquakes than its neighbors, but that might not be good news. In some cases, quiet parts of a fault mean that pressure has been building underground for a very long time, and when it gets released, a wave of destruction follows. What scientists fear most is something called a megathrust earthquake. It's the strongest kind of earthquake our planet can produce, and Cascadia is very capable of producing one. We're talking about an earthquake above magnitude 9. That kind of event releases insane amounts of energy. A magnitude 9 quake releases an almost unbelievable amount of energy, far beyond a magnitude 7. And compared to a magnitude 5, it's hard to even imagine the difference. If a megathrust earthquake happens in Cascadia, entire parts of the coastline will shift within minutes. And there's another terrifying detail most people never think about. The land itself might suddenly sink. Some studies suggest parts of the coast on Vancouver Island could drop by 3 to 6 feet during a serious Cascadia rupture. Imagine standing in a coastal town and, in mere moments, the ground beneath the entire area suddenly lowers close to sea level. just before tsunami waves arrive. Alarmingly, scientists have already seen strange warning signs underground. Back in 1999, GPS stations across the region detected something bizarre. Over a huge area, the ground briefly moved backward by about 0.8 inches. The movement was equal to a magnitude 6.7 earthquake, but nobody on the surface felt anything. There was no shaking or destruction. The Earth just moved soundlessly. Scientists now call these events silent earthquakes. Even when they happen, everything above ground seems perfectly calm. What makes the Cascadia Fault especially terrifying is that a disaster already happened there once. On the night of January 26, 1700, the entire coast broke apart. Deep offshore, the Cascadia Fault snapped loose and triggered a massive megathrust earthquake. The rupture stretched from Northern California all the way to Canada. The power of the earthquake was terrifying, somewhere between magnitude 8.7 and 9.2. And then came the tsunami. People in Japan actually recorded the event. Historical books describe a huge tsunami suddenly crashing into the coast, but nobody had felt an earthquake beforehand. They called it an orphan tsunami because the source was completely unknown at the time. No wonder, the earthquake had happened thousands of miles away across the Pacific Ocean. But that's not all. Along parts of the Oregon and Washington coasts, scientists discovered ghost forests, lifeless trees still standing in the sand. Those forests were ruined by salt water after the land dropped during the earthquake. Then the tsunami arrived and buried everything under sand and debris. Even today, during low tide, you can see the tree stumps sticking out of the beach. And there's more. Indigenous tribes along the Pacific Northwest coast passed down stories about that night. They described violent shaking during a winter evening, followed by enormous waves. Those waves wiped out entire villages near the shoreline. Only people living high above the water survived. Scientists believe those stories describe the same Cascadia megaquake. Megathrust earthquakes don't affect one small area. They move gigantic sections of Earth's crust. During the 2004 Indian Ocean disaster, a massive section of the seafloor suddenly shifted upward. The same thing happened during Japan's 2011 Tohoku earthquake, and Cascadia is capable of doing exactly that. But nobody knows exactly when the next rupture will happen. But experts think there's roughly a 1 in 8 chance of a Cascadia megaquake happening within the next 50 years. And if it happens, the scenario is terrifying. First, the shaking. Along the coast, people would feel minutes of violent ground movement. Older buildings would collapse and bridges would go down. Even worse, it would trigger landslides and liquefy the soil beneath many neighborhoods. In some places, the ground could behave almost like liquid mud. Parts of the coastline would suddenly drop by several feet. And after that, people would have only about 15 to 20 minutes before tsunami waves slammed into the shore. Some waves would reach 30 to 40 feet high. Some models suggest even worse. Walls of water approaching 100 feet in certain areas. Huge sections of coastline would flood for miles inland. The water wouldn't just hit once. Wave after wave would continue crashing inland for hours. Roads would disappear and entire communities could become completely cut off. For many people near the coast, there would be almost no time to escape once the shaking stops. That's why it's so important to learn more about the Cascadia Subduction Zone. If we don't fully understand how the plates are moving below the surface there, it will be much harder to predict where strong earthquakes can happen next. On January 26, 1700, one of the biggest earthquakes in history hit off the coast of the United States. It had a magnitude of 9, which puts it in the top 10 most powerful earthquakes ever recorded. This earthquake triggered a huge tsunami and changed the coastline all the way from southern British Columbia down to northern California forever. Back then, the area wasn't very populated, but thanks to some clever research, scientists figured out exactly what happened that day by looking at old geological records, tree rings, and even some history from Japan. On the same day as the earthquake, a massive tsunami also hit Japan's eastern coast. For a long time, no one connected the two, but in the 1980s and 90s, researchers realized the tsunami in Japan had been caused by the earthquake in the Pacific Northwest. They were also able to pinpoint the exact day, January 26, 1700. They even found old trees in coastal Washington that had all perished around the winter of 1700, which matched up perfectly with the timing of the earthquake. The earthquake came from the Cascadia Subduction Zone, a fault where the Juan de Fuca plate slides under the North American plate. This fault stretches about 700 miles, from northern Vancouver Island in British Columbia to Cape Mendocino in California. The pressure from the moving plates builds up over time, and eventually, another big, devastating earthquake will hit the same region. It's just a matter of time. By looking at the geological records, past tsunami deposits, and signs of land level changes, scientists can figure out how often these huge earthquakes happen. Emergency planners have been preparing for the next big quake, often calling it the big one. Scientists believe earthquakes in the Cascadia Subduction Zone happen every 200 to 1,000 years. And since the last major one was over 300 years ago, the Pacific Northwest is definitely due for another. When it happens, the earthquake is expected to be as big as the one from 1700. But this time, it'll affect around 15 million people. The devastation will be severe. Buildings will collapse, roads and runways will crack, and bridges will fall. Communication in and out of the area will be cut off. But the worst part? The earthquake will trigger a massive tsunami that might hit parts of the Washington coast in as little as 10 minutes. It's not a matter of if, but when the Cascadia Subduction Zone will break. When it happens, it will be the worst disaster the US has ever faced. Worse than the Hurricane Katrina or Superstorm Sandy. It'll impact an enormous area, stretching from southern British Columbia all the way down through Oregon to northern California. That means millions and millions of people will be affected. Fairchild is considered a backup staging area for handling the aftermath of the earthquake, with Grant County International Airport in Moses Lake being the main one. For those who will survive the initial quake and tsunami, the aftermath could be just as disastrous. Aftershocks will follow, and transportation will be a mess. Roads will be damaged or completely blocked, airports will shut down, and most of the main routes, like Interstate 5, will have bridges destroyed. This means food and water supplies will be cut off, and it will be incredibly difficult for help to get in or for people to escape. Gas pipelines will most likely be damaged too, and restoring them could take anywhere from a few days inland to weeks or even months along the coast. Power outages will be widespread within 100 miles of the coast throughout the entire Pacific Northwest. And water could be out for 3 to 7 months. Even telecommunications will be down for 2 to 3 months across the Pacific Northwest, Alaska, and even parts of East Asia. The good news for eastern Washington is that it will mostly avoid the worst of it, thanks to natural barriers between the west and east sides of the state. The tsunami may hit the Columbia River Gorge, but it will lose energy quickly because of a sandbar under the river. The Cascade Mountains will absorb much of the earthquake's impact, so the east side won't feel it as strongly. And since eastern Washington won't get hit as hard, it'll be up to them to handle the aftermath of the quake. That means helping western Washington, taking in refugees from the areas that got destroyed, and delivering supplies to where they're needed. Scientists have looked at other major 8.0 to 9.0 magnitude earthquakes like the ones in Chile in 1960, Alaska in 1964, and Sumatra in 2004, and Japan in 2011. These kinds of quakes can shake the ground for anywhere between 6 to 10 minutes, and that's a long time for the ground to be shaking. Such quakes are super intense because they happen close to Earth's surface, so it's not just a quick shake. It's a long, strong one that can cause a lot of damage. If the Cascadia earthquake and tsunami were to hit tomorrow, over 13,800 people could lose their lives. and about 107,000 people could be injured. The economic toll in Washington, Oregon, and California could top $70 billion. To put that into perspective, we can compare these numbers with some other major earthquakes. In Chile's 1960 earthquake, about 1,650 people lost their lives. The 1964 Alaska quake resulted in around 140 lives lost. The 2004 Sumatra earthquake and tsunami took the lives of an estimated 280,000 people. And the 2011 Japan earthquake and tsunami caused over 20,000 casualties. Authorities know about the dangers of the Cascadia Fault, but even with all the planning, no one can say for sure what will be needed when the big quake hits. Right after the earthquake and tsunami, the areas outside the immediate disaster zone won't be able to help much because roads and airports will be destroyed, and resources will be limited. How can we deal with this kind of disaster and its effects? We don't have all the answers yet. Right now, let's focus on the Cascadia Subduction Zone. It's a huge fault line that stretches about 620 miles from Vancouver Island to Cape Mendocino in California, sitting about 93 miles off the coast. It's like one tectonic plate is slowly sliding under another. When the plates are close to the surface, about 18 miles deep or less, they get stuck because of friction, kind of like pushing two rocks together. Over time, this creates a lot of pressure. When the pressure finally becomes too much, the plates slip, causing a massive earthquake. This is called a megathrust earthquake, and it can be huge. Below the area where the plates are stuck, there's a zone where the plates move really slowly. We're talking about just a few inches every few months. This slow movement helps to release some of the pressure, but it also builds up more pressure on the parts of the fault that are still stuck. This means that over time, it increases the chances of a huge earthquake happening. These massive quakes, called Great Subduction Zone earthquakes, can be stronger than magnitude 8.5. Megathrust earthquakes are the biggest earthquakes that happen. They can go over a magnitude of 9.0, which is insanely powerful. Just to put it in perspective, a magnitude 9.0 earthquake releases 1,000 times more energy than a 7.0 and 1,000,000 times more energy than a 5.0. These earthquakes happen when a lot of pressure builds up in a part of the fault that's locked, which means the plate can't move past each other. When that pressure gets too high, the fault finally ruptures, releasing all that built-up energy in one massive shake. The Cascadia Subduction Zone is super long. That's why if it were to rupture all at once, it could produce a large earthquake. Scientists have studied this region and found that about 18 miles below the surface, the fault is completely locked. The plates there aren't sliding past each other. But deeper down, the plates start to slide more smoothly, causing less friction. This is important because it tells us how much stress is building up in that locked zone, and how it could eventually lead to a major earthquake.
A network of deep faults runs right beneath Seattle, and it can shift at any moment, affecting millions of people. The consequences could be as catastrophic as in the past, when a devastating quake lifted the seafloor, collapsed shorelines, and triggered a massive tsunami. It happened in the winter of the year 923. A powerful earthquake hit what is now the Seattle area. It reached around magnitude 7.5, and the impact was terrifying. The ground didn't just shake violently, it shifted. Shorelines collapsed, parts of the seafloor lifted upward, and a tsunami swept through Puget Sound, flooding coastal areas. This event came from the Seattle Fault Zone. This is a complex system of faults that runs directly beneath modern-day Seattle, and it's still active today. This makes it one of the most dangerous geologic threats in the Pacific Northwest. Now, what threat does it present? Well, if a similar earthquake happened now, it would hit a densely populated region, putting millions of people at risk. It would also cause billions of dollars in damage to buildings, roads, and infrastructure. Scientists have started studying this fault more closely to understand how often it produces major earthquakes. They looked at the past 11,000 years to analyze time gaps between large seismic events. Well, the results are kinda mixed. On the one hand, devastating earthquakes, like the one that hit in 923, seem to be extremely rare. In fact, it's the only known quake of that size, magnitude 7.5 or higher, linked to this fault zone. So we can hope that the worst-case scenario, where massive earthquakes like this happen often, is unlikely. But researchers have also made a rather worrying discovery. Smaller earthquakes happen more frequently than expected. And while these quakes may not reach magnitude 7.5, they can still damage buildings, crack roads, disrupt utilities, and trigger landslides. In a modern city like Seattle, even a moderate earthquake can cause really serious problems. In other words, the region still faces regular seismic risk. The fault is active, the pressure builds over time, and the ground can move again. The real danger is the ongoing threat of smaller but still destructive earthquakes, and they may strike with little warning. Now let's take a closer look at the Seattle Fault Zone. It's this huge fault system sitting right under Seattle, a whole network that stretches about 46 miles from the mountains east of the city, all the way to the water on the west side. And yes, it runs directly under Seattle. It's a thrust fault, which means one chunk of ground is slowly pushing up over another. That pressure builds up for a long time, and then suddenly releases. That's when you get a big earthquake. Scientists didn't really start digging into this until the 1990s, when they noticed strange gravity readings. Plus, they found signs that a tsunami had hit the area about 1,000 years ago. All of that pointed to one thing: something catastrophic happened here before, most likely that huge earthquake back in 923. But there was a problem. The data they had managed to gather only went back about 5,000 years. This certainly isn't enough to see a clear pattern. So researchers decided to dig deeper and turn to something called marine terraces. These are old coastlines that got pushed upward by earthquakes and now form something like steps along the shore. Now, an important detail. The 923 earthquake lifted the land by about 26 feet. So scientists started looking for other terraces with the same kind of shift. They mapped out more than 150 of these terraces around Puget Sound, measuring their height and adjusting for natural slopes. It turned out that only one event in an 11,000-year window caused a big uplift like that: the 923 earthquake. As for smaller quakes, those could be hidden under layers of sediment. It means that huge city-shaking earthquakes are very rare, possibly with 5,000 years or even more between them. But it doesn't mean the danger is gone. Smaller ones are what we should worry about. They hit way more often, and they can do serious damage. That's why researchers focused on smaller side faults. Those are called blind faults because you can't see them at the surface, but they can still trigger strong earthquakes, and they already have. One of these smaller faults caused a magnitude 6.7 quake in the past. That's strong enough to damage buildings, crack roads, and mess up infrastructure. So the team pulled together a bunch of tools, like magnetic scans, fieldwork, LiDAR maps. They even dug trenches across fault lines and used dating methods to figure out when past quakes occurred. In the end, they found 3 more earthquakes. One happened around 11,000 years ago. One more hit in the early 1800s. That's a pretty big gap. But it proves these smaller faults have been active for a long time. But the most worrying thing is that these quakes didn't line up with movement on the main fault. That means the smaller faults can rupture on their own. When the team added all this new data together, they saw a pattern. Smaller quakes hit about every 350 years over the last 2,500 years. That's more frequent than scientists used to think. And this activity seems to have picked up over the last 2,000 years. Now, researchers are trying to figure out how big these quakes can actually get, how often they hit, and what would happen if one struck today. But it's not so simple. they have to piece the whole picture together from rocks, layers of soil, and tiny clues they find underground. So, where does it leave Seattle? Well, there's a national system called the Seismic Hazard Model. It's what engineers and planners use to decide how strong buildings need to be, how to design infrastructure, that kind of thing. Right now, this system includes the big 923 style quake, but it doesn't really account for the smaller side faults. First of all, these faults are shorter than what the model usually considers. Second, we're still unsure about how powerful their quakes can get. That's why the model should probably be updated, and authorities need to start planning for those more frequent quakes. It could directly affect building codes and safety plans. Now, despite this worrying news, there are other even more dangerous faults on Earth. Like the San Andreas Fault, it cuts through California for about 800 miles. It's where two massive plates slide past each other sideways. That constant grinding builds pressure and then releases it fast. That's how you get quakes like the 1906 San Francisco disaster. Today, millions of people live right on top of it, so scientists track every, even the tiniest tremor with sensors, watching for signs of a bigger break. Then, there's the North Anatolian Fault that runs about 930 miles across Turkey. It tends to break in a chain reaction, one quake triggering the next along the line. In 1999, one of those breaks hit Izmit and took the lives of over 17,000 people. Now the stress is building closer to Istanbul, and that's a city with over 15 million people. The Sumatra Subduction Zone in Indonesia is where one plate dives under another, locking up tons of energy. In 2004, it unleashed a magnitude 9.1 quake and a tsunami that more than 230,000 people didn't survive. It's still active today, and scientists constantly monitor the seafloor and ocean pressure to catch tsunami signals as early as possible. The Alpi Belt stretches over 1,500 miles from southern Europe to Asia. It once helped build mountain ranges like the Alps. Here, plates crash into each other and push land upward. Quakes don't occur here often, but when they do, they can be powerful and hit heavily populated regions. Japan also sits right where several plates collide. It's one of the most earthquake-prone places on Earth. In 2011, a massive offshore quake triggered a tsunami and the Fukushima disaster. Since then, Japan has built one of the most advanced monitoring systems in the world. Thousands of sensors track ground movement in real time to send out warnings within seconds.
Right now, as you read this, two colossal slabs of rock are locked against each other beneath the streets of Oakland, California. It sounds like nothing to an unprepared person, but the problem is that they're pressing harder with every passing year, storing up energy like a spring that's been coiling for more than 150 years. Roughly 30 feet below the sidewalks where people walk their dogs and grab their morning coffee, a geological clock has already run out. And scientists now know with uncomfortable precision exactly what happens when it finally lets go. This is the story of the Hayward Fault, one of the most dangerous strips of land in the United States, and the extraordinary computer simulations that are finally revealing the full picture of what the next big earthquake will do to millions of people. Let's start with the fault itself, because the Hayward Fault is not some distant geological curiosity hiding far out in the wilderness. It runs for roughly 74 miles right through the heart of California's East Bay, directly under neighborhoods, schools, hospitals, and highways, in cities like Oakland and Berkeley. More than 2 million people live or work along its path. And it is, by scientific consensus, overdue. The last time the Hayward Fault produced a major rupture was in 1868. That earthquake, estimated at magnitude 7, was devastating by the standards of the time. It flattened buildings across Hayward and sent shockwaves all the way into San Francisco. But here is what makes today's situation so much more serious. The fault average cycle between major earthquakes is around 140 years. We are now more than 150 years past that last rupture. The clock has not just run out, it ran out over a decade ago. The numbers from the United States Geological Survey make this concrete. There is roughly a 1 in 3 chance of a magnitude 6.7 or larger earthquake on this fault within the next 30 years. But the Hayward Fault doesn't operate in isolation. When scientists factor in connected faults in the region, including the nearby Rogers Creek Fault to the north, the probability of a major rupture somewhere in the system climbs to 72% by the year 2043. That is not a distant hypothetical. That is a near certainty within most people's lifetimes. So what exactly happens when it breaks? For decades, the honest answer was, we're not entirely sure. General earthquake models existed, but the Bay Area's geology is complex, a patchwork of hard rock, soft sediment, deep basins, and hill formations. And predicting how seismic waves travel through that maze was beyond the computing power available. That changed recently. Researchers at Lawrence Livermore National Laboratory and Lawrence Berkeley National Laboratory used some of the most powerful supercomputers on Earth to run 50 separate simulations of a magnitude 7 earthquake on the Hayward Fault. Each simulation varied the details, where exactly the rupture starts, how the slip spreads across the fault surface, how fast the break travels. The result is not one prediction, but a rich, detailed map of possibilities, showing not just where shaking will occur, but how intense it will be, how long it will last, and why certain neighborhoods face dramatically higher risks than others. What they found should reshape how every Bay Area resident thinks about where they live. The most important takeaway from these simulations is this: the ground does not shake equally. Location matters enormously, and the differences are not subtle. Take the Eastern Hills, places like Orinda and Moraga. These communities sit on layers of softer sedimentary rock, and that geology acts like an amplifier. In a major Hayward Fault earthquake, shaking in these areas could be up to 50% more intense than in western neighborhoods sitting on solid bedrock. That is not a rounding error. That's the difference between a building that survives and one that doesn't. And then there's Livermore Valley, which faces a different but equally serious problem. The valley sits in a geological basin, and seismic waves behave strangely inside basins. They bounce around, trapped between the basin walls, unable to escape. Instead of the shaking lasting the usual few seconds, simulations show it could continue for more than 2 minutes in Livermore. 2 full minutes of sustained, violent shaking. For pipelines, warehouses, and industrial infrastructure, that duration is potentially catastrophic. In Oakland and Berkeley, right on top of the fault line itself, the main danger comes from what scientists call directivity pulses. When a pulse ruptures, the break doesn't happen all at once. It races along the fault, and in doing so, it flings concentrated bursts of energy forward like a wave from a moving source. Communities directly in the path of that forward momentum get hit with sharp, powerful pulses that are particularly destructive to tall buildings. Skyscrapers and high-rises in these cities face the highest risk from this effect, with ground accelerations that can reach the equivalent of the full force of gravity. Enough to overwhelm structures that were not built with this specific threat in mind. Meanwhile, on the western side of the Bay Area, underlain by the hard Franciscan bedrock, things look noticeably different. Ground acceleration there could be 20 to 50% lower than in the highest risk zones. San Francisco itself will certainly feel the earthquake, but distance and solid geology provide meaningful protection. This does not mean western neighborhoods are safe. It means they are safer, relatively speaking. To understand why geology creates such stark differences, it helps to think about how seismic waves actually move. When a fault ruptures, it sends waves radiating outward in all directions. much like dropping a stone into a pond. But unlike water, the ground is not uniform. Hard bedrock transmits those waves quickly and efficiently, so energy passes through without lingering. Soft sediment, by contrast, slows the waves down, compresses them, and forces them to grow taller and more violent. The same way ocean waves rear up and crash when they hit shallow water near the shore. The Bay Area sits on an extraordinary variety of ground materials, which is precisely why two neighborhoods just a few miles apart can experience the same earthquake in dramatically different ways. The simulations capture this complexity in finer detail than any previous model, and the results make clear that geology is not just a background detail, it's the single biggest factor determining who gets hurt and who walks away. What makes these simulations genuinely groundbreaking is that they don't just produce abstract data, they produce actionable intelligence. Engineers can already use these results. For skyscrapers in Oakland and Berkeley, the pulse wave risk means buildings need reinforcement specifically designed to absorb those sharp, sudden jolts rather than the slower, rolling motion of distant earthquakes. In Livermore, foundations for new construction must account for extended shaking durations, not just peak intensity. In the eastern hills, slope stability becomes a critical concern. Steep hillside homes face elevated landslide risk when shaking amplifies. For public infrastructure, Bay Area Rapid Transit, BART, and the region's freeway systems are being prioritized for retrofitting based on the directivity cone maps and simulations produced. The fault doesn't just threaten buildings, it threatens the transportation networks people will desperately need after a major event. And for ordinary residents, the implications are personal and practical. Securing heavy furniture, water heaters, and bookcases reduces injury risk. Early warning apps can provide seconds of notice before shaking arrives, enough time to drop, cover, and hold on. Emergency supplies for at least 3 days are not excessive preparation. For a region this exposed, they are basic common sense. The science of earthquake prediction is moving fast. These simulations are already being extended to the San Andreas Fault, modeling potential magnitude 7.5 or larger events. Higher resolution subsurface mapping will push the models to even finer detail. But the Hayward Fault simulation already tells us something profound. We do not need to be helpless in the face of this threat. The ground beneath the Bay Area is not a mystery anymore. We know where the danger concentrates. We know why some neighborhoods will shake harder, why some valleys will shake longer, and why some buildings face risks that others don't. The question is no longer whether this earthquake is coming. The question is whether we will be ready when it does. A magnitude 15 earthquake has the potential to completely destroy our planet and evaporate all the water in a matter of seconds, leaving Earth uninhabitable. Over 500,000 earthquakes happen annually, but none have a magnitude of 15. 90% of quakes occur in the terrifying Ring of Fire zone located around the Pacific Ocean. The ground there is like jello. It shakes almost constantly. The most powerful earthquake to have ever struck Earth had a magnitude of 9.5. That much power can lengthen or shorten the day. But there's probably an earthquake in the confines of your own home now caused by a speck of dust landing on a table. But it has a power of negative 15 magnitudes. Earthquakes happen when tectonic plates move. They're like Lego pieces that are not properly secured, and when they move up, down, or hit one another, the ground also moves, triggering earthquakes. This tectonic energy acts like a battery. It stores energy for a long time, up to 500 years. When this stored energy is released in a sudden burst, the consequences are horrifying. Even the strongest structures submit to this relentless force that leaves a trail of destruction in its path. In some instances, earthquakes can even trigger tsunamis, amplifying the chaos. Such a crazy amount of power can split the ground open and cause severe damage. The strength of an earthquake is measured by the Richter scale, but now it's being replaced by the moment magnitude scale. When there's an earthquake, we hear about how strong it is. It's usually from 1 to 10. Luckily, we haven't had a Richter scale earthquake yet. The most powerful earthquake to have ever happened in modern history occurred in Chile in the 60s. It was around 9.5 on the Richter scale, and it altered Earth's rotation and messed up the length of the day by around 2 milliseconds. It also triggered a massive tsunami and affected a vast area of 155,000 square miles. The Richter scale doesn't actually have a limit. Still, anything above 25 doesn't need measuring, because if that ever happened, we would simply turn into dust, and nobody would care to measure this disaster. As we said, the strongest earthquake had a magnitude of 9.5. If this magnitude had been just 0.5 stronger, it would have created a ruptured line 2,174 miles long. That is almost 7 times the size of Wyoming. A magnitude 11 earthquake would create a crack halfway around the world. Massive tsunamis would hit coastal areas, destroying everything, and Earth would get into a massive environmental crisis. If you love hiking, you would have new mountains to explore, created by the terrifying earthquake. Even the temperature would increase because of volcanic eruptions and the resulting greenhouse gases. It would turn our planet into a hot oven. The safest places would be far away from any buildings, seas, oceans, and mountains where there would be a low chance of a landslide. Countries unprepared for earthquakes would be totally destroyed, and cities would turn into piles of rubble and dust. Going up on the Richter scale would only make things worse. But don't worry, an earthquake of that power is impossible. Earth's crust doesn't have enough energy to produce such earthquakes. But there is something that has much more power and can produce mega earthquakes. Asteroids are powerful enough to destroy our planet, as we all know from the dinosaur era. That asteroid was around 6 miles long, and it caused massive damage to the planet. It triggered earthquakes that shook the ground constantly for months. These terrifying quakes were about 50,000 times stronger than the Chile earthquake. They also triggered a tsunami that was 30,000 times more powerful than the Indian Ocean tsunami. And the latter was one of the most devastating tsunamis to have ever struck Earth. The earthquakes caused by the asteroid had a magnitude of 11, making it the most powerful and scariest natural disaster ever. And let's hope it stays that way. The Indian Ocean tsunami affected only certain areas of the world. Meanwhile, the asteroid tsunami affected every part of the world and had 33-foot-tall waves. Even if you had traveled to the most remote place on Earth, you wouldn't have been able to hide from this Grim Reaper. A 15-magnitude earthquake wouldn't be 15% stronger than the Chile earthquake. The scale doesn't work like that. It would be around 100 million times more powerful than a 9.5 magnitude quake. It could make all the water on Earth evaporate, leaving us devastated and without any H2O to survive. All ecosystems would collapse, all food chains would be broken, and only some super strong bacteria would probably survive the impossible. That is only a fraction of the frightening things that could happen. The ocean is like the AC for our planet. Without it, Earth would be super hot. The ocean also serves as a shield from the sun's powerful rays. It acts as a heat absorber and cools Earth. Scientists think that the most dangerous thing would be the inability of Earth's crust to survive the violent shakes of the 15-magnitude earthquake. If our planet miraculously survived and didn't turn into dust, there would be massive openings in its crust. The ground would become gelatinous. It would randomly move up, down, left, and right, and no building would survive that. Our civilization would be brought back to the Stonehenge era. Tectonic movements like this are devastating. A similar thing happened in Japan when tectonic plates moved 165 feet from each other and then snapped back together, creating a 9-magnitude earthquake. No place on Earth is immune to this bone-chilling natural phenomenon. Still, certain places have higher chances of being destroyed than others, like the Ring of Fire, where 90% of earthquakes happen. This is a place where earthquakes are almost everyday occurrences. The Ring of Fire is located in the Pacific Ocean. It forms a ring around the continents that surround the Pacific. There, several tectonic plates meet, creating highly unstable ground. To make the problem much more terrifying, 75% of active volcanoes are located in this area. 90% of dormant volcanoes are also there, making this place extremely dangerous. Scientists carefully study this region to find a way to predict when the next earthquake might strike. The Ring of Fire is not the only place at risk of earthquakes. In California, along the San Andreas fault line, two tectonic plates have been storing power for more than 200 years. The San Andreas Fault is 715 miles long and has the potential for a massive earthquake. This region has its fear of violent earthquakes like the one that happened in San Francisco in 1906. It had a magnitude of 7.8 on the Richter scale. Scientists' predictions are terrifying. They say that the chance of a 6.7 magnitude earthquake is very high in the area. If all hell starts to break loose, you should know how to survive. Avoid anything that might fall on you, like windows, closets, or unstable ceilings. The official phrase from emergency experts is drop, cover, and hold on. Stay low to the ground. Hide under something stable like a table, and remain there until the shaking stops. Make sure to stay in your shelter for another minute or two, just in case there are aftershocks or loose debris. Use your nose and smell for gas. If you do smell it, don't turn the lights on or do anything that might ignite it. Stay strong and be safe.
So, since 2000, the world has been hit with more than 1,700 earthquakes with magnitude greater than 5. Many happened around the Ring of Fire, located around the Pacific Ocean. In North America, the biggest threat is the San Andreas Fault Line, which can create an earthquake of a magnitude higher than any other, earning it the spine-tingling nickname, the Big One. The potential destruction of California is a terrifying prospect that could have unimaginable consequences. But the Big One is just the beginning of what's to come. Bad news! Scientists have predicted an earth-shattering event that will occur in 2030. Like it or not, there's a 70% chance that we'll experience the Big One, and it will be an earthquake with a magnitude of 6.7. The San Andreas Fault Line will cause the Big One, but what is scary is that we can't predict it. On the other hand, a massive earthquake occurs every 100 years. This means there's always time to prepare for a natural disaster. If we traveled back in time, we'd see a few significant earthquakes like the ones that wiped out San Francisco and Fort Tajon. Buildings made a long time ago are not quake-proof. They will collapse. Even if they survive, you should not enter them. But buildings are not the most dangerous part. You should watch out for electrical lines and gas pipes. Your hill house might be lovely, but it is extremely unsafe. During quakes, the hill can turn into a massive landslide that will destroy everything in its path. Say goodbye to road trips because all the roads will be ruined. You should have some spare water and food since you won't be able to go to the supermarket. This disaster won't be cheap. It will cost the U.S. around $200 billion to recover from the quake. At least the earthquake will not trigger tsunamis. But there's something it can cause more damage than the Big One. The notorious Cascadia Subduction Zones start in California and ends up all the way in Vancouver, Canada. The San Andreas Fault Line is nothing compared to this zone. It can wipe the whole coast off the face of the Earth, an example of hyperbole. Subduction zones are tectonic plates forced to be one under the other and constantly pulling apart. One is called the North American Plate and the other is the Juan de Fuca Plate. Zones like these are not to be messed with, since they are terrifying hotspots for earthquake activity and extremely dangerous because they cause massive underwater quakes. But they are underwater, so what can they do to us? Well, they can cause giant tsunamis, flooding cities, and destroying the coastline. Right now, the most active zone is the Ring of Fire. The Cascadia Zone might be less active, but it is like a sleeping beast that can wake up and destroy everything in its path, causing a groundbreaking earthquake. The last time all this stress was released was in the year 1700. Unlike the San Andreas quake, this one will cause massive tsunamis and much bigger shocks. Let's hope you'll be camping in an open field at that time, because most buildings and bridges will likely be destroyed. Also, be ready for the aftershocks, as they'll be devastating. Nature won't be spared either. Landslides will change animals' habitats. Even our homes will be changed forever. Luckily, there is a light at the end of the tunnel, and scientists are doing everything they can to ensure our safety. New rules are implemented. Every new building must be able to withstand massive shocks. They're developing modern warning systems, and every new infrastructure must follow strict quake-proof guidelines. The Juan de Fuca and the North American plates are locked together, but they won't stay like that forever. When they unlock, get ready for a massive shake. The closer you are to the epicenter, the more damage you'll experience. But even if you are lucky to be far away, you may still feel the ground shaking for some time. Now, if we compare the Cascadia Subduction Zone and the San Andreas Fault, we'll see how much more dangerous the Cascadia Zone is. In 1994, there was an enormous 6.7 magnitude earthquake in the Northridge area, close to the San Andreas Fault. Sadly, many people didn't make it, and some were injured. Back then, buildings were not strong and earthquake-proof, and many of them were damaged. The Cascadia Subduction Zone can potentially cause a magnitude 9 earthquake. A magnitude 6 quake has the power of around 44 million pounds of dynamite, but a magnitude 9 has the power of 44 trillion pounds of dynamite. The strongest ever recorded quake was in Chile. Its magnitude measured 9.5, and it destroyed most everything. So let's say you've survived the quake, but the struggle is far from over. Soon after, a massive tsunami will strike, with waves that might reach up to 100 feet in some areas. That's so unlike the San Andreas earthquake, which can't produce any significant waves. So say goodbye to your beautiful garden, since salt water will destroy trees and plants, changing the environment for a period of time. The only positive thing will be you won't need Halloween decorations, because all those dried-out trees will resemble a ghost forest. The combination of waves, quakes, and the sheer size of the area will make this natural disaster much more dangerous than any caused by the San Andreas Fault or the so-called Big One. A quake similar to this happened around 300 years ago. Many more have been recorded in the past 3,500 years, proving that they continually occur every 400 to 600 years. So, technically, we have around 100 to 300 years before the next big one hits. We still have no idea how exactly the Cascadia Subduction Zone works, because we discovered it in 1970. This zone is super scary because it can cause big earthquakes. It was found by accident when researchers studied the Ring of Fire. They wanted to know if this area had caused any trouble in the past years, and the proof was under their noses. In Washington, there is a horror forest where nothing has been growing for years. When researchers tested the soil, they found a tremendous amount of salt. They put 2 and 2 together and concluded that a massive tsunami had been the reason. Experts still didn't know when the forest was destroyed, but Japan kept records of a gigantic earthquake that had a similar effect. It was the one that happened in the year 1700. There is a 1 in 3 chance that the next one will occur in 2050. You must know how to survive the Canadian earthquakes and make it out unscathed, so listen carefully. Those who live in this area have almost no experience with earthquakes like this one. Surviving the quake is relatively easy, but the tsunami coming afterwards is the real danger. After the shake, find the highest ground and go there. Only bring the essentials, like food and water. Yeah, leave your baseball card collection at home. After the first hit, don't try to go down. Seismologists say that most likely there will be a few more waves, and they have proven this. On the 22nd of May, 1960, seismologist Jerry Eston and his 4 friends went to Hawaii to see an expected tsunami that was to happen around midnight. They set up their gear on Wailuku Bridge with an escape route planned. This bridge had been destroyed in the previous tsunami, but the new one was much taller and better. After midnight, the water was 4 feet above the average level. The second wave hit a half hour after midnight, and the water rose another 9 feet by 1 a.m. The water started going down and dropped by 7 feet, but the horror was far from over. Next, they saw a wave that was around 20 feet tall. This shows us that tsunamis are unpredictable, and we should listen to experts to stay safe.
The floor is lava. Haha, just kidding. But honestly, it's kind of falling apart. You might not feel it yet, but a huge part of North America has already lost 37 miles worth of rock from its foundation. And no, this isn't about earthquakes or giant sinkholes. It's about the continent losing pieces of the very thing that keeps the ground from wobbling around like a bad carnival ride. A team of researchers has just dropped a geological bombshell. Part of North America's ground is thinning out like a very sad, very slow ice cream drip. How do they know? They basically gave Earth a high-tech full-body MRI and created 3D maps showing how rocks once considered indestructible are now melting away into the planet's guts, like an upside-down cheese pizza inside an oven. But to really understand this mess, you first have to meet my old friends, cratons. Cratons are like the roots of the continents. They're thick, tough, and ancient. We're talking billions of years old. These bad boys survived meteor impacts, supervolcanoes, and even the tectonic movement of plates. If the plates got into fistfights, for example, you can bet we would see mountain ranges being born. If they got a divorce, drifting apart from each other, then a whole new ocean would be born. All of these things leave scars on the surface of Earth, but the cratons seem to always remain unfazed, like the cockroaches of geology. And since a craton can basically get punched in the face and feel nothing, scientists always assumed these things were nearly indestructible. But then, a group of researchers took their fancy machines to the test and realized that, wait, the cratons are falling apart? How? Enter the Farallon Plate, a really ancient tectonic plate that started to slide under North America's major plate over 100 million years ago. This is a pretty normal process, actually. It's called subduction, and it's how Earth recycles rocks and keeps itself from overheating. This subduction thing has been happening for so long that, by now, the Farallon is almost 400 miles away from the craton, sitting pretty chill at the lower mantle, weirdly close to the outer core of our planet. But the Farallon has been causing trouble, like that one roommate who moved out but keeps leaving weird stuff in the fridge. You see, as it sinks, it tugs on the bottom of North America's foundation, stretching it out and causing pieces to fall off into the deep mantle. And if that wasn't enough drama, the sinking Farallon has also leaked water and carbon dioxide into the surrounding rocks, making the craton even softer and easier to shred apart. Thanks, Farallon. Very cool of you. By studying hundreds of earthquakes across thousands of monitoring stations, scientists have confirmed the story. Big chunks of continental material are dripping downward, thinning the craton by as much as 37 miles. That's more missing rocks than can fit into a milk carton. Sounds dramatic, right? But don't worry. This is happening at a snail's pace. It'll take millions of years for anything noticeable to happen. Your great-great-great-great few grandkids from the distant future might still be standing on solid ground. But don't get too comfy. This thing may not be an urgent problem, but there's another type of sinking that's happening faster than you can say, "Help!" Here's the thing. By 2050, at least 32 major cities in the US, including New York, Baltimore, and Charleston, could be partially underwater. And guess what? This one is mostly our fault. Scientists noticed that since 2007, some cities have been sinking into the ground between 0.04 and 0.08 inches every year. Charleston, in South Carolina, is pulling ahead in the worst way possible, sinking 0.15 inches annually. Sure, these numbers sound tiny and a bit ridiculous, but Charleston is barely 9 feet above sea level, and a little sinking goes a long way when the ocean is breathing down your neck. On really bad flood days, people there have to abandon their cars and basically swim home. This whole phenomenon is called land subsidence, and when you mix sinking land with rising sea levels, you get a disaster cocktail of flooded streets, salty farmland, ghost forests, and a lot of very cranky homeowners. And it doesn't stop with just homes. Infrastructure like bridges, roads, airports, and power plants, all things we rely on daily, are also at risk of serious damage. Flooded electrical grids and sunken highways could cause billions more in economic losses and create major safety hazards for communities. Now, let's be fair. Not everything is humanity's fault. Some of this trouble dates all the way back to the Ice Age. About 12,000 years ago, massive ice sheets covered the northern US. They were heavy, like seriously heavy. The weight pushed the land down, and when the ice melted, the ground didn't just pop back up like a trampoline. Instead, it started playing a weird game of geological seesaw. The places that were squished started rising, and the places that weren't got pulled down. This whole process, called glacial isostatic adjustment, try to say that 3 times fast. But of course, humans found a way to make it worse. Groundwater extraction is a major culprit. Think of it like pulling the stuff out of the mattress. After a while, the whole thing just sags. In places like California's Central Valley, the land is dropping by up to 8 inches a year because we keep pumping out water during droughts. In cities like New York, the problem isn't just water. Skyscrapers themselves are making it worse. Yep, turns out if you stack millions of tons of concrete and steel onto soft ground, it tends to flatten. And in case you're wondering, the total mass of New York City's buildings is around 1.68 trillion pounds. That's about the same as 3.5 million statues of liberty piled up. With so much weight concentrated over a relatively small area, the underlying soils have no choice but to compress over time. And if you thought it couldn't get messier, think again. We've been building dams, which stop rivers from delivering fresh sediment to coastal areas. That sediment is kind of like Mother Nature's way of fluffing the ground back up. Without it, coastal lands are compacting like an old sponge. Plus, when wetlands are drained for agriculture or construction, the peaty soil dries out and collapses. Honestly, it's like the ground just can't catch a break. Scientists also noticed that the areas that used to be lush wetlands are now among the fastest sinking spots in the country, especially along the Gulf Coast. Louisiana, for example, is losing about a football field of land because of this mix of subsidence and rising seas. So what's the endgame here for us regular people who just want to live above sea level? Well, it's not looking great. Ghost forests, which are basically drowned woodlands, are popping up. Farmland is turning salty and unusable. And even sunny day flooding, where streets flood without any rain, is becoming a thing. Yikes! Meanwhile, over on the West Coast, California is not exactly winning either. San Francisco and Los Angeles are both sinking, which means that rising sea levels could hit them twice as hard and twice as fast. In some places like the Palos Verdes Peninsula, the ground has been sinking so fast, people over there might as well live like moles. So, is America turning into the next Atlantis? Probably not next week, but without serious action, like cutting back on groundwater pumping and planning smarter cities, at least 500,000 people are in serious danger. And the housing damage could easily rack up a jaw-dropping $109 billion by 2050. In the end, while North America isn't about to sink like a poorly made souffle, it's definitely showing some cracks in the crust. So maybe let's ease up on groundwater pumping, rethink how and where we build, and invest a little more in keeping our feet dry. After all, if the floor really does become lava someday, we're gonna wish we had at least fixed the leaks first. Something is about to reshape the entire future of the West Coast. The coastline, the infrastructure, the whole map. Scientists fear there is not one but 2 big earthquakes coming, one caused by another. This wasn't even on the radar for most people, but new research is changing everything. For decades, everyone treated the San Andreas Fault and the Cascadia Subduction Zone like 2 separate monsters that just happened to live in the same neighborhood. They were powerful, yes, but independent. But now, scientists believe these 2 giant faults are mechanically linked, and one can literally pull the other into rupturing shortly afterward. Cascadia moves, San Andreas moves. San Andreas tears, Cascadia tears. And the potential consequences of that are honestly haunting. scientists found evidence that it happened at least 10 times in the last 3,100 years. Earthquake. Pause. Earthquake. It comes from marine sediment cores, which are like time capsules pulled up from the ocean floor. Researchers analyzed layer after layer of seabed sediment and found doublets. Paired debris layers created by two massive quakes happening so close together that the ocean barely had time to settle between them. That discovery takes us to the Mendocino Triple Junction, the geological troublemaker of the West Coast. It's the place where three tectonic plates crash and grind into each other like badly aligned gears. It's also the zone where the San Andreas meets Cascadia, which makes it the perfect place for these double quakes to form. The stress changes caused by a rupture in one fault travel straight through this junction and destabilize the other. It's benign when it happens to a bookshelf. When you move one book, three others shift. But when you think about it like a coastline with millions of people, entire cities, major infrastructure, it instantly feels terrifying. To many people who live on the West Coast, the San Andreas kind of feels like a California's problem, and Cascadia like an Oregon and Washington's problem. But when you understand that these two faults can essentially fire at each other, it stops being a local issue and becomes a continental one. A Cascadia megaquake alone can hit magnitude 9.0 plus, rip open 600 to 700 miles of seafloor, and send a tsunami roaring toward the Pacific coast. And it could just be the first quake, and then, maybe minutes later, the San Andreas snaps in Northern California. The shaking could ripple down the state like a zipper tearing open a jacket, and if it goes the other direction, it could be just as bad. If the San Andreas ruptures first, the intense stress redistribution can destabilize the Cascadia Subduction Zone. You could get the California quake first with buildings rocking, highways breaking, and power stations failing. And then, soon after, the ocean pulls back in Oregon or Washington. And the 20-minute countdown to a tsunami begins, a follow-up disaster. It's the kind of chain reaction you don't want even in a video game, let alone real life. This discovery also tells us something eerie about the earthquake in 1700, the one that sent a tsunami across the Pacific so huge that it struck Japan with no warning. Japanese fishermen called that wave the orphan tsunami because it arrived without any felt shaking. Only centuries later, scientists figured out that it came from the Pacific Northwest. But until recently, no one knew that the San Andreas might have felt that event too, and it possibly slipped or destabilized because of it. So, the whole West Coast may have moved together. And we've come to the scariest part. All this isn't about if, it's strictly about when. The faults have a rhythm, a pace, and a geological heartbeat. We've seen how they behave across thousands of years. We know what they did, and now we know they sometimes do it in sequence. The real fear isn't the first quake. California already expects a big one. The real fear is the second quake, the one that comes before you've checked on your family, before emergency responders regroup, before the power comes back, and before the dust settles. Even if you don't live on the West Coast, this matters for you too. The ports in California, Oregon, and Washington handle a massive chunk of America's imports. Knock them offline, and it's not just the coastline that feels it. The ripple hits the entire country, and potentially the world. Grocery prices spike, supply chains freeze, gas availability dips, shipping timelines go nuts. The world is much more connected than any of us thought, and a geological double punch on the Pacific coast wouldn't stay a local disaster. It would spread, thread by thread, into everyone's life. So, those in power must prepare not for one giant rupture, but for two. Emergency plans, evacuation routes, response times, and power grid designs, all of it needs updating. Because nature has now shown us what even a single major rupture can do to a modern economy. It happened in Japan in 1995, on January 17th at 5:46 in the morning. The quake hit right by the northern tip of Awaji Island, only 12 miles from Kobe, a huge, busy city with about 1.4 million people back then, and another 2.6 million in Osaka nearby. The rupture ripped along the Nojima Fault, for about 25 miles. That doesn't sound like much until you realize entire buildings can't survive that kind of sideways shove. More than 5,000 people lost their lives. 43,000 were injured. Nearly 400,000 buildings were irreparably damaged. This disaster hit one of Japan's largest industrial zones. And when you mess with a place like that, the shock doesn't stop at the shoreline. The damage was $200 billion US in losses, from smashed buildings and infrastructure and many businesses shutting down. Kobe's port just collapsed. Only 30% of the Osaka-Kobe railway lines worked. Part of National Route 28 literally vanished into the ground. Schools, hospitals, and municipal buildings, 85% of them took damage or were unusable. Fires broke out across Kobe, almost 300 separate incidents, burning the equivalent of 70 US city blocks and taking another 600 to 700 lives. Almost 100,000 people permanently left the region, 2.5% of the whole population gone in less than a year. And here's a detail that stuck with me. So many bridges failed that engineers suddenly had to confront how poorly older designs handled lateral shaking. Houses with heavy tiled roofs, built to fight typhoons, crumbled because all that weight sat too high. But the newer homes made after the 1981 building code revision stood. And that's when Japan realized that modern seismic standards were crucial to follow. Japan threw $58 billion US into restoring the region. Power came back in days. Roads and rail returned in 5 to 8 months. The main expressway took 21 months. The port was fully rebuilt in just over 2 years. And by then, all debris was cleared. Within 15 months, manufacturing jumped back to 98% of its old level. Stores reopened. By 1999, Kobe's economy reached roughly 75 to 90% of pre-quake levels. Japan overhauled its disaster management system entirely. They set up the Central Disaster Management Council and rewrote building codes. They upgraded everything from emergency drills to fire-resistant city layouts, and they launched the Earthquake Early Warning System that now gives Japan those precious few seconds before shaking hits. The same system that saved countless lives since 2007. But despite all this improvement, the Kansai region still sits on dangerous ground. The Roku Awajishima fault system, the same one that snapped in 1995, still runs under them. The 2018 Northern Osaka quake and the 2024 Noto Peninsula quake reminded everyone that this threat didn't disappear. It just waits its turn. A future large event on that system could hit even harder simply because the region has grown more complex, more interconnected, and more economically loaded. So Kobe wasn't even a triggered double fault rupture, but it still broke a major industrial hub, reshaped a national economy, and permanently changed global shipping routes. That's why when scientists started talking about two joint faults firing off back-to-back in Cascadia and San Andreas, you don't even have to imagine the consequences. We already got a preview in 1995.
There is a powerful force hiding underground where tectonic plates meet, and one forces another under it. This happens in the Pacific and Indian Oceans. Strain builds over centuries. The tension is unbearable until the megathrust awakens. The Earth shakes with a magnitude that can exceed 9 points, more powerful than any other earthquake. When the seafloor suddenly gets pushed up fast, it sends a huge ripple across the water, and a tsunami of huge force is out. These waves are called teletsunamis, and they cross entire ocean basins, ready to take over coastlines thousands of miles away. The thrust fault stretches over 600 miles. The Earth is not just shaking, it feels like it's tearing apart. This is the power of a megathrust earthquake. Those caught in its path will have to fight for their lives. Japanese authorities recently had to issue their first ever megaquake advisory. It happened because of a strong tremor on the edge of the Nankai Trough ocean floor zone. In the end, most of the warnings were lifted, and there wasn't much damage from the 7.1 magnitude earthquake. Parts of southwestern Japan started to shake, and the superfast trains in Japan slowed down to stay safe, which made travel slower for everyone. But everyone is staying alert as they know about the risk of a megathrust earthquake that could happen within the next few decades in the Nankai Trough. The tectonic plate under the Philippine Sea is slowly sliding underneath the land where Japan is, moving just a few inches every year. The last big earthquakes from this area happened in 1944 and 1946, both with a magnitude of 8.1. These quakes have caused a lot of destruction in the country. The next megathrust earthquake in the region, if it does happen, could be between a magnitude 8 and 9. Scientists still can't agree on how likely this mega earthquake is to happen, but it could be up to 80% certainty. On the other side of the Pacific, scientists from the U.S. Geological Survey have studied a dangerous area along the U.S. West Coast. It's called the Cascadia Subduction Zone, and it stretches from northern California to northern Vancouver Island in Canada. Over the past 14,200 years, there have likely been at least 30 big earthquakes in this region. One major quake happens every 500 years on average. But for a long time now, Cascadia has been quiet, and it worries scientists. They think this might be because the area is locked, meaning the tectonic plates are stuck together and building up a lot of pressure. Eventually, the part of the seafloor could suddenly break and move by several feet. The shaking would be just 5 minutes, but it would create a powerful tsunami as the seafloor shifts that would last for 10 hours. If it happens, it's going to be the worst natural disaster in the country's history, according to experts. The ground on some inland hills could turn into something like quicksand. This would cause the hillsides to slide and crumble, taking down roads and bridges. Around 620,000 buildings could be badly damaged or even collapse, including about 100 hospitals and 2,000 schools. People in Washington state might have to take care of themselves without help for 2 weeks, finding food, water, and shelter on their own. Scientists are studying slow slip events, where the tectonic plates move very slowly over weeks or months, releasing some energy but not enough to stop a big one. Every time the magnitude of an earthquake goes up by just one number, the energy it releases is 40 times bigger. So we'd need about 1 million small earthquakes every day for 500 years straight to release the same energy as one huge magnitude 9 earthquake. But these small earthquakes might be clues that a bigger earthquake is coming. To better monitor the Cascadia Fault, experts are mapping the fault more accurately and adding better monitoring tools offshore. Scientists receive over $10 million to install seismic sensors and seafloor pressure gauges on a fiber optic cable off the coast of Oregon. The goal is to be ready to warn people and potentially save lives when a big earthquake strikes. A sharp megathrust earthquake happened in this part of the world in 1964. It went down in history as the Great Alaska Earthquake and had a magnitude of 9.2. It lasted for more than 4 minutes, making it the most powerful earthquake in the history of the U.S. and North America. The ground shook so hard that it caused huge cracks and landslides. In Anchorage, many houses, buildings, and roads were destroyed because they weren't built to handle such a big earthquake. In some places, the land was permanently changed. For example, the coastline near Kodiak and Hinchinbrook Island was lifted by 30 feet. In other areas, like Gerwood and Portage, the ground sank by 8 feet. They had to rebuild roads higher so they wouldn't be flooded by the tide. A huge 27-foot tsunami wiped out the entire village of Chiniga. Many coastal towns were heavily damaged, not just by the earthquake, but also by tsunamis and the fires that followed. After the main earthquake, there were thousands of smaller aftershocks for months. A moderate earthquake of magnitude 4.4 shook Los Angeles in August 2024. Once it was over, the LA Fire Department checked around the city and didn't find any major damage or anyone hurt. In the nearby city of Pasadena, which is close to the earthquake's epicenter, a water pipe burst inside City Hall and everyone had to leave the building. Thankfully, there was no danger of a tsunami. The best we can do to avoid panic in such situations is to be prepared. Japan is one of the places on Earth where earthquakes happen the most, because it sits on the edges of 4 tectonic plates. Around 1,500 of these earthquakes each year are noticeable. Because of this, the people in Japan have learned to live with earthquakes. The 1950 law set a rule that buildings should be able to handle earthquakes up to a magnitude 7 without falling apart. An update 30 years later said that buildings should only have minor damage in such earthquakes and still work as usual. But if an earthquake is even stronger, the law says the building's main job is to not collapse and save people's lives. At the most basic level, buildings are made stronger with thicker beams, pillars, and walls so they can handle shaking better. Another technique is placing special pads made from materials like rubber at the base of a building. Some buildings are even built on thick layers of padding that separate them from the ground completely, which helps protect them during an earthquake. A skyscraper might sway back and forth a lot, moving up to 5 feet. To stop it from getting damaged, engineers can add something called dampers every second floor all the way to the top. These dampers are like giant bicycle pumps, but instead of air, they're filled with liquid. When the building shakes, the dampers push against the liquid inside them. Even though the liquid doesn't squish very much, it can still absorb some of the shaking. When they're building tall skyscrapers, engineers try to make the structure as simple and balanced as possible. This means having each floor the same height and placing the support columns evenly. But sometimes, architects who design skyscrapers don't want to make these compromises because they have creative ideas for how the building should look. Then they have to find compromise solutions. For example, Tokyo's Skytree Tower, one of the tallest buildings in the world, is designed in a futuristic style but also includes special features to protect it from earthquakes. It has a central pillar, like in traditional Japanese pagodas, and seismic dampers that help absorb the energy from an earthquake, keeping the building safe.
An earthquake in Indonesia began in 1829 and lasted a mighty 32 years. It reached its climax in 1861 and hit a magnitude of around 8.5. It was caused by the tectonic plates below the island slowly clashing against each other. Researchers discovered that the quake had been building for some time after analyzing the coral in the area. They found it was being periodically exposed to the open air. That was caused by the gradual earthquake moving the land up and down. Scientists call these decades-long silent earthquakes slow slip events. A single lightning bolt can warm the air to around 54,000 degrees Fahrenheit. The heat makes the air expand quickly, creating a shock wave or boom, which we know to be thunder. There are close to 3 trillion trees on Earth. That translates to roughly around 422 trees for every person. Before humans, the number was nearer to 6 trillion. Almost 70% of the Earth's surface is covered by water, which on average is around 2.5 miles deep. 97% of Earth's volcanoes lie underwater, as well as the mid-ocean ridge, a massive mountain range that is over 40,000 miles long. Humans have mined around 190,000 tons of gold from the planet. Experts predict there is around 20% still left to be mined, but this figure is constantly changing. The world's largest active volcano is in Hawaii. Called Mauna Loa, it's over 2.5 miles above sea level. Given that most of it is underwater, the volcano's summit is a staggering 11 miles from its base. That's the same length as over 160 football fields. The highest ever recorded temperature on Earth was a sweltering 136 degrees Fahrenheit. It was recorded in El Azizia, or modern-day Libya, on September 13, 1922. The lowest temperature was a chilling minus 129 degrees Fahrenheit, recorded at Russia's Vostok station in 1983. Earth is the 5th largest planet in the solar system, behind Jupiter, Saturn, Uranus, and Neptune. It has a circumference of roughly 25,000 miles, and it would take the average person around 8,300 hours to walk around the face of the Earth. The separation between Earth's land masses would make such a trek almost impossible, though. It takes 365.25 days for the Earth to orbit the Sun. Because our calendar years only have 365 days, we add an extra leap day every 4 years to make up for the difference. Russia is the largest country on the planet, with a total area of about 6.5 million square miles. It encompasses more than 1/8 of the Earth's inhabited land area, but still has a relatively small population given its size. Earth is the only planet with one moon. Mercury and Venus have no moons, while every other planet has 2 or more. Earth is over 4 billion years old. Scientists calculate this by looking at the planet's oldest rocks, as well as meteorites that have crash-landed. They used meteorites as they were formed at the same time as Earth, when the solar system was forming. The ground we walk on is basically recycled. The planet's rock cycle turns igneous rocks to sedimentary ones, then transforms those into metamorphic rocks, and back again. Like Earth, our moon also experiences earthquakes. They're less common and intense than the ones we have, and are caused by tidal stresses. A tidal stress is basically the relationship between the gravitational pull of the moon on the Earth and that of the Earth on the moon. Despite being the 5th largest continent, Antarctica holds 70% of the planet's fresh water and about 90% of its ice. Bangkok is the most visited city in the world, boasting 23 million visitors in 2019 alone. Paris, London, Dubai, and Singapore make up the other cities in the top 5. The lowest layer of Earth's atmosphere is called the troposphere and is the reason we have weather. Sunlight heats the planet's surface, which causes warm air to rise up to the troposphere. This air then expands and cools as the air pressure decreases and sinks down, where it is then warmed by the Earth again. Coral reefs are the largest living structures on the planet, with some even being visible from space. Coral reefs hold the most species per area of any of Earth's ecosystems, even more than rainforests. Earth got its name around 1,000 years ago, and it comes from the German word meaning the ground, but there's no evidence to show who actually named it. Of all the planets, Earth is also the only one which is not named after a Greek or Roman deity. The deepest point of the ocean is the Mariana Trench. It's a whopping 7 miles below sea level. Coastlines cover about 20% of U.S. land, but are home to more than 50% of the U.S. population. The Earth isn't actually a sphere. It's more like a squished ball that bulges at the equator. The bulge is caused by the force of the Earth spinning, which makes the north and south poles slightly flat. The Earth spins on its axis, which is basically an imaginary straight line. Earth has seasons because the axis is tilted, causing the sun's rays to hit different parts of the planet more directly, depending on the time of year. If the sun was as tall as a standard door, the Earth would be around the size of a nickel. The Earth's rate of rotation is gradually decreasing. It's happening so slowly that it would take as much as 140 million years for the length of a day to increase to 25 hours.
Get equipped for any season with brand new Brightside merch. Click the link and grab your print.
The biggest animal on Earth is the Antarctic blue whale. It can reach lengths of 100 feet and weigh up to 400,000 pounds, which is around the same as 33 elephants. The temperature at the center of the Earth is around the same as the surface of the Sun, at almost 10,000 degrees Fahrenheit. Earth is around 10,000 times older than humans. Earth is around 4.5 billion years old, whereas humans have been around for, at most, 450,000 years. There are around 34,000 known species of fish. The actual number is way higher though, as a whopping 95% of our oceans still haven't been explored. America's Route 66 is longer than the journey to the Earth's core. The distance to the core is roughly 2,000 miles. Route 66 is almost 2,500 miles. The Earth is made up of 3 main components: the crust, the mantle, and the core, which is divided into the outer core and the inner core. Scientists have estimated that there are around 8.7 million species on the planet. Out of this, between 1 to 2 million of these species are animals. But roughly 86% of land species and 91% of fish have yet to be discovered by humans. Ancient astronomers used to think that the Earth was the center of the universe. For 2,000 years, they believed the Earth to be static, while other bodies traveled in orbit around us. In 1543, Copernicus published his sun-centered model of the solar system. Earth is the densest planet in the solar system. The density varies across its different crusts, but the planet's average density is just over 3 ounces per cubic inch. Mount Everest is the highest point on the planet. Its peak is the highest altitude above sea level at around 5.5 miles. Each year, 1 septillion crystals of snow fall on Earth. That's a trillion snowflakes. Snow covers about 31% of Earth's land area each year. Of Earth's water, only around 3% is fresh water. The other 97% is salted. Of that 3%, about 2% is frozen in ice and glaciers. So, less than 1% of the planet's fresh water is actually in lakes, rivers, and underground. The world's largest inland body of water, or lake to us normal people, is the Caspian Sea. It has an area of 140,000 miles squared. The world's deepest lake is Lake Baikal in Russia and is 5,300 feet deep. Earth's atmosphere is roughly 78% nitrogen and 21% oxygen, with small amounts of water vapor, carbon dioxide, and other gases. No other planet is believed to have this much oxygen, which explains why Earth is the only planet where life has been discovered so far. Apart from the Moon, there are 2 asteroids in co-orbital orbits with Earth, sometimes called Earth's second moon. 3753 Cruithne is an asteroid that looks like it's following the Earth in orbit, but it's actually following its own path around the Sun. 2002 AA29 is another asteroid which makes a horseshoe orbit around the Earth that draws it close to the planet every 95 years.
The strongest earthquake ever to strike east of the Mississippi River that happened over 200 years ago was never over, according to some scientists. Most earthquakes last seconds to minutes, and the official record breaker so far is a silent one in Sumatra that was going on for 32 years. This slow slip event triggered a massive quake and a tsunami. So if it's true that the New Madrid earthquake is still sending aftershocks, we'll have a new top name for this sad list. The earthquake started in December of 1811 with a powerful quake in a sparsely populated part of northeast Arkansas. They felt the shaking almost 1,000 miles away in the White House, and the tower bells were ringing in Boston, even further away. It even made the mighty Mississippi flow backward for a few minutes over new waterfalls formed by shifted ground. The town of New Madrid, Missouri, completely disappeared in the disaster. The Earth wouldn't stay still until the end of January the following year, when things got serious again. A massive quake hit, this time near the junction of the Ohio and Mississippi rivers, right in the Missouri boot heel. Geologists believe it was a rupture on the New Madrid Fault, putting even more strain on the nearby Reelfoot Fault. Just when people thought it couldn't get worse, another 2 weeks of trembling passed, and the Reelfoot Fault snapped deep beneath New Madrid. Down in Tennessee, about 15 miles south of New Madrid, the ground uplift created Reelfoot Lake. Steamboats were chugging along the river, with thousands of trees floating and acres of woods torn apart by the quake. In St. Louis, Missouri, which is 160 miles away, buildings were badly damaged, and chimneys fell in Cincinnati, Ohio, 400 miles away. People all the way in Montreal, Canada, over 1,000 miles away, felt the earthshake. Seismologists have registered about 200 small earthquakes in the New Madrid seismic zone every year since 1974. Some researchers believe that up to 30% of those were aftershocks from those big quakes back in 1811 and 1812. In parts of the U.S. where there's not much tectonic action going on, these aftershocks could keep rumbling for years, maybe even centuries after the big ones hit. Aftershocks are the Earth's way of releasing all that built-up stress from the main quake. When the ground shakes from the first earthquake, it puts a lot of pressure on the rocks nearby. And when those rocks can't take it anymore, they crack, causing even more shaking. That's the aftershock. And they can be pretty intense, especially right after the main quake, but weaken over time. Not all scientists agree that contemporary earthquakes have to do with those from 200 years ago. We mostly associate faults with those lines where Earth's plates meet. But there's a whole network of those right under the center of the North American plate. They're like relics from 750 million years ago, when North America was part of a supercontinent called Rodinia. When Rodinia started to break up, it left behind these rifts, weak spots in the Earth's crust that run deep beneath the modern Midwest. It could explain the earthquake action. An international team of geologists decided to take a fresh look at 3 major earthquakes that shook North America and end the debate. They used a new math method called the nearest neighbor. It says that if earthquakes are too close in space, time, and magnitude to be independent background events, then one is assumed to have triggered the other. Depending on how you look at the numbers, somewhere between 10 to 65% of the recent quakes in the region could be aftershocks of those historic earthquakes. And a huge quake that hit Charleston, South Carolina at the end of the 19th century might explain up to 72% of the earthquakes in the area since then. But not all places are the same, so the scientific debate continues. In 1774, British explorer James Cook noticed a glow in the distance. It was the volcano of Mount Yasur in Vanuatu. This bad boy had been spewing lava and ash ever since, and it's quite likely that it's been doing that for way longer. The volcano has been sitting at alert level since October 2016, which means things are really unsettled around there. They've even marked off a 2,000-foot radius around the crater to keep people safe. There have been low to moderate outbursts, shooting out ash, gas, and steam, and some bigger blasts throwing stuff outside the crater. Satellite images have picked up on some hotspots of sulfur dioxide plumes, showing that Yasur is still cooking up a big storm down there. Stromboli, one of the volcanic islands near Sicily, officially has the Guinness World Record as the longest continuously erupting volcano. It has been putting on a fiery show for over 2,400 years straight. Ancient sailors nicknamed it the Lighthouse of the Mediterranean. Most of the time, Stromboli's just spitting out spatter, but every now and then it throws in some lava flows or shoots up some moderately high fountains. Sometimes you might even catch a glimpse of steam-driven outbursts. Over 200 million years ago, the world went through a major makeover, with not 1, not 2, but 4 massive volcanic eruptions changing the game. It all happened in Rensselaer, a large chunk of island that used to be a supermassive volcano stretching across what's now British Columbia and Alaska. This volcanic activity might have helped dinosaurs grow from cat-sized critters into giants we saw in Jurassic Park. It kicked off a 2-million-year rainy season. It made the whole world hot and humid, and the dinos just loved it. Researchers dug deep into sediment layers beneath an ancient lake in China to uncover these secrets. They found traces of volcanic ash and mercury, clear signs of those epic eruptions. There were carbon signatures showing huge spikes in carbon dioxide levels, making the atmosphere toasty and the rain pouring down. It all happened in 4 separate pulses, each triggered by those monstrous volcanic blasts. There's a spot in a national park not too far away from Sydney, Australia, where a fire has been raging deep underground for at least 6,000 years. They call it Burning Mountain, and it's a coal seam fire, burning its way through a layer of coal beneath the Earth's surface. Once these underground fires start, they're pretty much impossible to put out. This ball of fire is up to 30 feet wide and extremely hot, but there's no flame, it's smoldering. The fire has been creeping along at a pace of about 3 feet per year. A local farmer first spotted it in the 19th century and thought it was a volcano. The people who have lived here for ages believe this place is sacred. They've used it for cooking and crafting tools, and tell that it started from a widow's tears or the torch of a hero. But experts think it could have been a lightning strike or coal heating up like a summer barbecue from the interaction with oxygen. Some say it might have been burning since before the dinosaurs roamed the Earth. No one knows exactly how long this mountain will burn or in what direction it'll move. Right now, the coal has enough oxygen to burn for centuries or even millennia without human intervention. The fire is heating up the mountain like a giant oven, making it crack and crumble, inviting in more oxygen to feed on. Even if humans decide to take action, these coal seam fires need truckloads of water and liquid nitrogen to tame them. Several years ago, explorers noticed that the smolder was creeping close to a cliff overlooking a little river, and depending on what the coal seam decides to do next, we could see some dramatic changes here in the coming decades. There could be flames with much more heat, or the coal seam could go deep, extinguish itself, and smolder out.
We are on the Sea of Marmara, the exact spot where the massive continents of Europe and Asia meet. It's a vital, beautiful waterway packed with cargo ships on the surface, but dive underneath and you'll find a geographical nightmare lying on the seafloor. Deep underwater, two massive slabs of the Earth's crust are violently grinding past each other. This isn't just a minor crack in the dirt, it's a colossal geological fault. A massive complex system of continuous fractures that has been accumulating a devastating amount of energy for decades. We call it the Great North Anatolian Fault. All this energy has to be unleashed someday. And when it happens, it's going to hit one of the most densely populated areas on our planet. Scientists are now in active monitoring mode, especially when it comes to Turkey. This country is sitting on the Anatolian Plate, a small bite of the Earth's crust. Nowadays, it's being literally smashed by the Arabian Plate from the south and the Eurasian Plate from the north. Because it's being squeezed so hard, the only direction it can move is west toward the Aegean Sea, and it actually does this at a speed of about 1 inch per year. In geological terms, that's a high-speed, violent movement. Millions of tons of solid rock grinding against each other deep underground day and night without a single break? Not the best thing to experience. All this endless moving, cracking, and squeezing is what creates the North Anatolian Fault, a 930-mile-long fault line that acts almost exactly like the infamous San Andreas Fault. Yet the difference is striking. While the San Andreas mostly skirts the outer edges of Californian megacities or runs through less dense regions, the fault in Turkey is running right under major industrial hubs and heavily populated urban centers. In February 2023, the smaller sister of it, the East Anatolian Fault, showed us how dangerous this tectonic setup can be. It generated the most catastrophic earthquake recorded in Turkey in over 60 years. A brutal 7.8 monster hit and a 7.5 shockwave followed right behind it just hours later. The release of energy was so violent that the ground literally moved by almost 10 feet in some places. Entire cities were leveled and the physical map of the region permanently shifted. Now the worst part, it wasn't even the grand finale. There's no way to stop that energy packed inside the North Anatolian Faults. Look at the old data and you'll see it acts like clockwork, a bit like a line of falling dominoes. Scientists have been tracking every sequence of earthquakes in this region for nearly a century. The whole chain reaction started in 1939 with the catastrophic Erzincan earthquake. A massive magnitude 7.8 struck eastern Turkey. It didn't simply release the energy, but also transferred this tectonic stress into the next section of the fault. Dominoes started falling. Other fault rupture happened in 1942, 1943, and 1944. It went west and struck again in 1957 and 1967. Year by year, the epicenters of these massive earthquakes moved in a straight line toward the Sea of Marmara. The last major impact was the Izmit earthquake in 1999. A magnitude 7.6 tremor struck east of Istanbul and lasted for 37 terrifying seconds. Suddenly, the chain reaction took a break, but the tectonic stress was still there, simply transferred to the next section of the fault, under the Sea of Marmara, where the last major earthquake took place in 1766. Nobody had seismographs back then, but historical records and old journals describe it as a scene of unimaginable horror. Now, modern science tells us exactly why it was so devastating. Scientists are calling it a seismic gap, basically a dangerously quiet zone that hasn't ruptured yet. Back then, 260 years ago, a massive quake destroyed a huge part of Istanbul and generated a tsunami that crashed into the city's ports. After this tragedy, it didn't happen again on this scale, but we have to remember that the Anatolian plate has never stopped moving west, an inch a year. Let's do some quick math. That land should have moved by over 19 feet by now, but because those rocks are locked together, they haven't moved an inch. We are looking at a massive backlog of tectonic tension. It simply has to snap finally, and it won't make a regular shake. It will likely rapidly release 2.5 centuries of accumulated tectonic energy, right at the doorstep of Europe and Asia. The target is the city of Istanbul once again. We should call it a supercity because this global mega hub is home to an astonishing 15 million people. It accounts for nearly 30% of Turkey's entire economic output. What about the infrastructure? We're talking about 1 million buildings, and an estimated 90,000 of those are at high risk of total collapse in the event of a magnitude 7.5 earthquake. Nowadays, the city has very strict laws for modern buildings. But plenty of urban areas had been built before those regulations were enforced. To make matters worse, many coastal neighborhoods are built on soft, waterlogged soil that acts like a liquid during extreme shaking, multiplying the danger for the residents. Buildings could just sink into quicksand. And there's more. The seafloor of the Marmara Sea isn't flat. There are 3 massive deep underwater holes separated by vast ridges. Why is it important? A stronger earthquake in this area will probably trigger a massive submarine landslide. Plenty of mud and rock collapsing down those underwater canyons would instantly displace massive amounts of water. This would trigger a tsunami, not as tall as mega tsunamis in the open Pacific Ocean, but still highly dangerous. It's estimated that with a 10-foot wall of water, it will be extremely dangerous for this densely populated area. Scientists also claim that it could hit the coastline within 10 minutes. There would be almost no time for a mass evacuation. Here comes modern technology. Engineers are fully aware that this geographical clock is ticking and are fighting back. Essentially, infrastructure is being heavily retrofitted. Also, the mighty bridges crossing the Bosphorus Strait have been reinforced with seismic dampers to absorb extreme shocks. One of the world's largest seismically isolated buildings is located at Sabiha Gökçen International Airport in Istanbul. It's sitting on massive bearings made out of rubber and steel. The absolute art of engineering is the Marmara Tunnel, a massive railway tube that runs directly under the Bosphorus Strait, physically connecting the European and Asian continents underwater. It was built right next to an active fault line, so it had to be designed with flexible earthquake-proof joints. If a megaquake hits and the continents shift, the tunnel will bend and flex like a giant snake rather than snapping in half. Another concern of scientists is the economic aftershock of this rupture. It may affect the entire globe, as the Bosphorus Strait is one of the world's most critical maritime choke points. Every single year, nearly 50,000 ships pass through this narrow waterway, carrying everything that is crucial for the global market: barrels of oil, agricultural goods, and so on. The price of energy and food would go crazy if this shipping line collapses. To buy some precious time, scientists have installed an advanced early warning network on the seafloor of the Marmara Sea. Fiber optic cables and seismometers are constantly listening to the fault. But because the epicenter is located so incredibly close to the city, even this multi-million-dollar system won't give residents enough time to escape. At best, it will provide a maximum of 5 to 7 seconds of warning before the destructive waves hit the city. 5 seconds to shut down gas lines, halt the trains, and brace for the impact. Of course, all this effort won't protect the whole city. Only a fraction will survive. The undeniable conclusion is that the migration of earthquakes isn't just a theory, but a well-documented geographical reality. Scientists estimate that there is a 65% probability of a magnitude 7 or greater earthquake striking the Sea of Marmara region before the year 2030. Now we can see that the rupture in this area isn't just a possibility. It is coming, and it is migrating directly toward the collision point of two continents.